In this video, we're going to be discussing Newton's laws of motion. Now, these laws are formulated by Sir Isaac Newton. They laid the foundation for classical mechanics. We also explore the mathematical formulas associated with each of the laws. So let's start with the first law. The first law of Newton's first law states that an object at rest will remain at rest. An object in motion will remain or will continue in motion with constant velocity unless acted upon by an external force. This law is also known as the law of inertia. So for the first law, Fe, which is the net force, is equal to 0, which means that an object at rest, it remains at rest. An object in motion remains in motion if the velocity remains constant, right? And then there is no external force acting upon it. Okay, now please keep that in mind. Let's go to the second law. Newton's second law states that the acceleration of an object is directly proportional to the net force and is inversely proportional to the mass, right? So for Newton's second law, we say the net force, it's equals to ma, right? So we say that the acceleration is directly proportional to the net force. Acceleration A is directly proportional to this net force and is inversely proportional to what? The mass, right? Now we know that A, which is acceleration, is equals to final velocity minus initial velocity divided by change in time. So this is just like the change in velocity all over change in time, right? So now you can carry this particular equation and replace it here. So we now have F now is going to be equals to V minus V naught all over T. This can also be equals to M. You just put delta V all over T. You can equally put delta T, right? Please keep all these formulas in mind. We know that momentum, which is written with a small letter p, is equals to mass times velocity. So momentum is usually measured when the object is in motion. So if something is not in motion, if there's no velocity, if your velocity is 0, if its object is at rest, it doesn't have momentum, right? Now, when you find the difference of momentum, so we're going to say the mass of velocity, right? Now you see the change in momentum is the same as a mass. You see mass change in velocity, mass change in velocity. So you can replace momentum to this. So you can say force now is the net force is equals to change in momentum all over change in t, right? Another formula I want us to look at again is finding the impulse, right? Now for the impulse, we know that when force is equals to mass change in velocity all over change in time, right? Multiply both sides by time, by t, right? By change in t. Here it cancels. So we have change in t, force is equals to mass change in velocity, right? And we know that force times change in time is equals to impulse. Right? And this side, we know that this is equals to momentum. So please keep all these formulas in mind. We're going to use them as we proceed. Now for Newton's third law. Newton's third law states that for every action, there is equal and opposite reaction. This means that if an object exerts force If object A exert force on object B, then object B will exert equal and opposite force on object A. So we say if object A, right, exert force on object B will have equal and opposite force. Because it's opposite, we'll put negative. That's equal and opposite force. So please, let's just use all of these and try some examples so you understand much better what I'm talking about. So here's our first question. Now, the question says, a force of 200 Newton is applied on a 10 kg box across a frictionless surface. A. So what is the acceleration of the box? B. If the box accelerates from rest, what will its final speed be after 8 seconds? C. How long will it take the box to reach a speed of 500 meters per second if it continues to accelerate at this rate? Right? So let's go with question 1. Let's start with A. For A, first we have a 10 kg box. So let's draw the diagram. This is our frictionless surface. We have a 10 kg box, right? 10 kg. Now, a force of 200 Newton is applied on this box, right? Now, a force of 200 Newton applied on a 10 kg box. The question is, what is the acceleration? So we know that from Newton's first law, F is equals to what? ma, right? Where F is a force, m is a mass, and then we're looking for acceleration. So therefore, A now is going to be equals to F all over m, which is going to be equals to what? 200 Newton all over 10 kg, right? A now is going to be, this cancel this, it's going to be 20 meter per second square. Hope you've taken down the question. For B, the question says, if the box accelerates from rest, right, what will be its final speed? What will its final speed be after 8 seconds? So now from the formula of acceleration we did earlier, we say acceleration A is equals to change in velocity all over time, right? This is final velocity all over time. Now, therefore, when you take this, you're going to say V final is equals to V naught plus AT, right? Now, therefore, we are looking for final velocity. We know that the initial velocity is 0 because it starts from what? Rest. Therefore, final velocity will be equals to, we know time to be 8 seconds, and then our acceleration we've already calculated, that is 20 meter per second square. So this is going to be 0 plus 20 multiplied by 8 seconds. Now, therefore, we have 20 times 8 is going to be 160 meter per second. So this is our B. Now for C, it says, how long will it take the box to reach a speed of 500 meters per second if it continues to accelerate at this rate, right? So we know that the final velocity, now v, for v, we have v final velocity, initial velocity plus at, which is what acceleration and time. Now in this case, we are looking for the time it will take for it to what, reach the final velocity of 500 meters per second if it continue at this to accelerate at this rate. So in this case, we know that the box started at rest, so the initial velocity is 0. So final velocity here is 500 meters per second is equals to 0, which is the initial velocity, plus we have 20 meters per second, which is per second square, which is the acceleration, and then we have t, time. So now we say 20 t is equal to 500, right? Divide by 20, divide by 20. T now is going to be equals to 25. 25 seconds, right? And to do that easily, you can say this divided by this, 50 divided by 2 is 25. The next question. So question says, a force of 300 Newton is applied across a 200 kg box. The frictional force acting on the box is 200 Newton. A. Calculate the net horizontal force on the box. B. Calculate the acceleration of the box. C. How far will the box travel after 12 seconds if it continues at the rate starting from rest? Now, question A. Let's draw a diagram first. These are horizontal surface, right? Now we have a 20 kg mass, a box of 20 kg. Then we have a force that is applied. We have a 300 Newton force. Then we have a frictional force. This will be capital PF. Then we have a frictional force. Let's use small f. A 200 Newton frictional force, right? Acting on this particular box. Now we are asked that what is the horizontal force on the box? Now the horizontal force on the box, we have 200 Newton frictional force acting in opposite direction, trying to stop the box from moving. Now we have a force, the box itself carrying a force that is applied across the box is 300. So we have 300 minus 200. So the horizontal force will be the net force. And the net force is equal to what? 300 Newton minus 200 Newton, which is going to be what? 100 Newton. This is the horizontal force. Hope you've taken down the question. So let's go to B. So B, they say that we should calculate the acceleration of the box, right? So we have the final force we know is 100. So acceleration is going to be net force is equals to mass times acceleration. Now we know that acceleration now in this case is going to be net force all over mass. Now we know that force, the net force is 100 newtons. And then we know the mass of the box is 20 kg. Therefore, acceleration is going to be what? 5 meter per second square. Right? Let's go to C. So distance D is equals to V naught T plus half acceleration T square. Now, we know that the distance here, distance is what we're looking for. V naught, in this case, V naught is 0, so everything here will be 0. Because anything times 0 is 0. So we have 0 plus half. Acceleration, we know is what? 5 meter per second. And then the time, we know is 12 seconds. Don't forget to put the square. Therefore, we know that this is going to be half 5, 12 times 12. 2 divided by 12 is going to be what? 6. So therefore, we have 5 times 6 and times 12. This 5 times 6 is what? 30. Right? Now, 30 times 12 is going to be what? 30 times 12 is going to be equals to 360. So, the box traveled 360 meters in 12 seconds. So, feel free to hit the subscription button to hit us the thumbs up. Let's take another question. Question 3. So the question says, a 80 kg object speeds up from 20 meter per second to 50 meter per second in 6 seconds. What is the acceleration? That's A. B. What is the net horizontal force acting on the object? C. If the frictional force is 35 newtons, what is the applied force on the object? So let's start with A. For A, we are looking for what? The acceleration. And we know acceleration is equals to change in velocity Vf change in velocity Vf minus V naught, right? All over T. Vf, which is the final velocity, is equals to what? 50 minus 20 divided by T. T, which is what? 6 seconds, sorry. Let me put the 6 seconds. So therefore, 50 minus 20 is equal to 30 divided by 6. So acceleration is going to be 30 divided by 6, which is what? 5 meter per second square. So this is going to be what? A. So let's look at B. B says, what is the net horizontal force acting on the object, right? For Newton's second law, from Newton's second law, we know force is equal to what? Mass times acceleration. Now, in this case, we know that the mass of the object is 80 kg, right? So the mass is 80 kg, and then we know that the acceleration A is equal to 5 meter per second square, right? Therefore, the net horizontal force is going to be 80 times 5, which is going to be 400 newtons. C. Now, for C, it says if the frictional force is 35 newtons, what is the applied force? So let's draw a diagram. So this is our horizontal surface. This is our mass, right? Mass of 80 kg. Now we have a frictional force of 35 newtons, right? We have a net force of 400 newton. Now what we're looking for is our applied force. So applied force FA is going to be equals to the frictional force plus the net force. So it's going to be F plus F net. Therefore, this is going to be 35 newtons plus 400 newtons, which is going to be equals to 435 newtons. And this makes sense because in order for the object to accelerate, the applied force must be greater than the word frictional force. And we know that the difference between applied force and frictional force is what gives us what? The net force. So this is our applied force. Let's take another example. Question number 4. So the question says, an 80 kg astronaut in space throw a 2 kg package with acceleration of 4 meters per second square. What force did the astronaut exert on the package? That's A. B. What force does the package exert on the astronaut? C. What is the acceleration of the astronaut? So now, solution. A, it says, what force did the astronaut exert on the package? So let's draw a diagram. Let's say these are astronauts. Right? Has 80 kg. Now it throws a package. This package is what? 2 kg. Now the acceleration of this package is plus 4 meters per second square. Right? Now to calculate the force the astronaut exert on the package, we use what? F is equals to FA. That's from Newton's second law. Right? Therefore, we know that the mass of this package M is equals to what? 2 kg. And the acceleration is plus 4 multiplied by 4. So what we have now is going to be what? 8 newtons. Alright, that is the force the astronaut exert on the package. So let's put A. So let's put B here now. For B, we're looking for the force the package exert on the astronaut. Right? So let's still use this our diagram here. Right? Now, in this case, we know that the astronaut exerted 8 kg newtons. Right? 8 newtons. Sorry, not 8 kg. 8 newton. The force is 8 newton on the package. Now, you know from Newton's third law, they say for every action there's equal and opposite reaction. So we know that the package will also exert 8 kg, 8 newton, I don't know, I'm using kg, 8 newton force on the astronaut. But in this case, it is going to be what? A negative. Right? Now, therefore, now to find the acceleration, to find the force that is exerted on the astronaut, you just look at the force the astronaut exert on the package, and then you get the opposite direction, because what, from Newton's third law, say for every action there's equal and opposite reaction, right? So let's just turn this to be C. Now for C, it says that what is the acceleration of the astronaut? Now to find the acceleration of the astronaut, we still use the formula from our second law of Newton, F equals to ma, and then we know that acceleration is going to be equals to what? Force all over what? Mass. Therefore, acceleration in this case, we know force of the astronaut is what? Minus 8 Newton. The mass of the astronaut is what? 80 kg. Right? So when you do the arithmetic, minus 8 divided by 80, what we have is what? Minus 0.1 meter per second square. Right? Now, I want you to note this. The object with less mass have larger acceleration when the force is constant. So you see we have 8 Newton and 8 Newton. The force is what? Constant. So therefore, the object with less mass will have what? Greater acceleration. Whereas the object with more mass will have what? Less acceleration.